Hello, welcome to today's seminar. Today's speaker is Adam Wagner from University of Illinois, and he will be giving us a tutorial to the container method.
Okay, so hi everyone, thank you for inviting me. So my talk is called Container Method Tutorial. That's because I'm going to try to teach you the basic methods, basic techniques that involve this method basically. So I'm not going to give you a precise proof of the container theorems. I'm not going to go through the algorithm of how to construct these objects. Instead, I will try to only focus on building some intuition. I will show you what kind of problems you can solve with this method and how these proofs roughly look like. So instead of being very precise, I will just try to build intuition, and the goal is that in the future, if you see a problem like this, then you can recognize it, oh, that I can apply the container method to it. And once you know that you can apply containers, you can actually go and read the papers and fill in the details yourself. Okay, so what is this container method? Just very, very brief history. It started with Kleitman-Winston in the 70s. So actually before that, it was the main ideas were present in the work of Saxton-Thomason already, but really it started with Kleitman-Winston in the 70s, and later on, so they proved some very nice theorems with this method, and after that, kind of for 3 decades, everyone forgot about this method, until very recently, when in the 2010s, 2 groups of authors, Balogh-Morris-Samotij, and Saxton-Thomason, these 2 groups of authors independently took the ideas of Kleitman-Winston, pushed it further into hypergraph settings, and that's when this method really became really powerful. Okay, so what are the types of problems that you can solve with the container method? So, what is the basic problem type? Okay, so the first ingredient you need for such a problem is you need to have a property that you're interested in. Property P. That could be a set property, a graph property, a property of families in the Boolean lattice, whatever property you want. But you need this property P to be monotone, and the most important, this P should be very easily characterized by what kind of stuff is forbidden. So this should be easily characterizable by what kind of stuff is not allowed in your object, by forbidden things. So we'll see some examples in a second, okay? So once you have this property, the most basic question that you can try to attempt to answer with container method is how many objects have your property P? How many objects satisfy P? If this is the question you want to answer and your P looks like this, then the container method was made for you. Okay, so let's see some examples.
Can you describe what you mean by monotone?
I think the best thing to do is to show you some examples, and you will see what I mean by that.
So this is something different than minor monotone?
I don't know what minor monotone is, so probably it is different. I have no idea what minor monotone is.
Well, you know what a graph minor is.
Yes.
Okay, minor monotone just means that the parameter can't go up as you take a graph minor.
All right, so minor monotone is a subset of monotone then.
Okay.
Yeah. Okay, so let's see some examples. So let's see some examples for such property. Can anyone tell me some kind of monotone properties? So by monotone I just mean that if a family satisfies this property, then every subfamily of it also satisfies this property. So can you try to tell me such a property?
Planar.
Planar. Oh, that's always the example that I get. I will just put it down here. That's because it's actually a non-example, but it's a very, very good answer. We will see why this doesn't actually fit into this category in a second. Okay, so
So planar is minor monotone.
I will get back to planar in 1 second.
Okay.
Okay. So another example that's not planar.
Triangle free.
Very good. Yeah.
Oh,
Very good.
much better guess.
Such a good guess. Yeah. Okay. So triangle free. Being triangle free is a monotone property because if a graph is triangle free, then every subgraph of it is also triangle free. And it's also very easily characterized by what kind of stuff is forbidden, because what is forbidden? Triangles are forbidden. That's the perfect match for this description. So if the question is, how many triangle free graphs are there? How many triangle free graphs on n vertices? Then this is a perfect match for the container method. You can answer this question very, very easily.
So monotone is subgraph monotone, the parameter doesn't go up when you take a
Subgraph monotone, that's right.
Okay. thank
But this property doesn't have to be a graph property, so that's why I just say monotone. So we could be talking about families of sets.
you. Okay,
or
but
any
for
object.
subgraphs, we can think of it as subgraph
Yes,
monotone.
absolutely. Yeah. You're not talking about any minors here. Okay, any other examples?
Colorable? K-colorable?
So K-colorable is a monotone property, but it's not very easily characterized by what kind of stuff is forbidden. It's not a local property whether a graph is K-colorable or not. So that's why it's not quite the right example. But good guess?
Bounded maximum, or bounded degree?
Yeah, I guess so. I never thought of that, so could be. So degree at most 5. Yeah, I guess so. Okay, some other examples that I did think of were, for example, Antichain, this is basically the standard example that if you want to learn containers, then you have to apply containers to antichains, and that's how you will understand the method. So antichain is a monotone property because every subset of an antichain is an antichain, and it's characterized easily by what is forbidden because comparable pairs are forbidden.
Could you define an antichain?
Yeah, antichain is just a subset of two Boolean letters, so F subset of 0, 1 to the n, such that there are no AB in the family with A subsets B. So these objects are forbidden. These are called comparable pairs, and we don't want them to be in the family. And if your family doesn't contain a comparable pair, we call it an antichain. Being an antichain is exactly a property that satisfies these things here. So the question of how many antichains are there in the Boolean lattice is the perfect question for the container method. Okay, let's just see a couple more examples. So, for example, you could have, or anything else?
Poset free.
Yeah, poset free. So you fix a poset, fix some poset p, and how many p free subsets of the Boolean lattice? Of course, answering this question gets more and more difficult if your poset becomes more and more complicated. So as long as your P is easy, you can answer the question easily. But once P gets some weird kind of poset, it gets very difficult. Okay, and the same thing works for, instead of triangles, you could say how many H-free graphs, where H is some fixed graph. Okay, but there are also different examples.
Could you do independent sets in a graph? I guess you need to know what the graph is.
So you fix a graph, how many independent sets are there in the graph? Oh, that's a really funny question.
Well, I'm going to and see if you get the same results as the entropy method, but I guess you'd have to run it on each graph. So
I cannot answer this question right now. I can think about it after the talk. It's a really funny question, actually. I would say no, it won't work, but I don't know why not. So, a couple more examples just quickly. So, for example, how many families in the Boolean that have no solution to here you can just put in any equation, for example, A symmetric difference B is equal to 17, or A union B equals C, or A intersection B equals C union D intersection E, whatever. So how many families are there that do not have a solution to some kind of fixed equation? All of these problems fit into this description, basically. Of course, again, more difficult the equation gets, more difficult it will be to apply continuum method. One last example before I get to the planar one is error correcting codes. How many 5 error correcting codes are there? On n bits, for example. So being an error correcting code is basically just being a subset of the Boolean lattice again, and it's also a monotone property because it just boils down to not having two code words at distance less than or equal to 10 from each other. So that's what 5 error correcting codes is. It's just a subset of the Boolean lattice that doesn't contain two code words at distance 10 from each other, unless I'm saying something stupid. So it's a monotone property, and it's very easily characterized. Don't contain two code words that are close to each other. So answering this question turns out to be very easy with the continuum method as well. And the reason why planar is not a good example, because yes, it's true that you can characterize easily by saying that you have no K5 minor and no K33 minor, but this word minor is actually tricky to grasp. So, of course, it's just one word, but it's actually a pretty long definition. I think that's the reason why actually trying to go through the calculations just doesn't work out. Maybe I'm just not good enough to answer this question with this method. I couldn't do it. And I have no idea how to do this question with this container method. Okay, so I think we have seen enough examples, so let's talk about how you can actually solve all these problems. And the good thing about this list of problems is that you can solve basically all of them in the exact same way. It's always the same 3 stages of the proof that you have to go through. And if you manage to go through these 3 stages, then you will get a reasonably good answer to your question. So, how to solve these problems? Using container method. So every container method proof contains these 3 stages. First step is always prove an upper bound on the size of your family. That satisfies your property. So for example, for triangle-free graph, every triangle-free graph has at most n squared over 4 edges, so that would be your upper bound. For antichain, every antichain has size at most n choose n over 2, so that would be your upper bound, and so on. That's always the first step. And the second step is this tricky one. It's this step called supersaturation that you might have heard of. So you need to prove that if you take a family that's slightly too large to have this property P, then it will contain many, many of your forbidden objects that you forbid in this second step. So you have to prove that if a family or graph is too large to be in P, then it contains many forbidden objects. So what does it mean? For example, in a triangle-free case, it would mean upper bound was n squared over 4 edges. So you would have to prove that if a graph has slightly more than n squared over 4 edges, then it suddenly contains many, many triangles. This is what the supersaturation means. Similarly for, if you pick any equation here, if a family is larger than the upper bound, then it will contain many solutions to this equation. And what we mean by many, that depends on the problem.
So I guess, Adam, that's why the minor thing is so difficult. When you try, you have, say, slightly more than the number of edges, how can you prove that you have many minors?
I don't think that's the reason why it's so difficult. That might be one of the reasons, I totally agree. Yeah, that actually sounds very difficult to prove this. Getting the codegree properties right would also be kind of a nightmare. So pretty much everything breaks down there for some reasons. Okay, so once you have the supersaturation, last step is apply the container algorithm. I'm not going to tell you today what this really is. So for now, I want to just treat it as a black box, and at the end, if I have time, I will get back to this. And basically, this container algorithm transforms the first two steps into a good counting result. So this is how I like to think of this container method. So I like to think of this as a big black box, the container method machine. It has two inputs. Here you put in your upper bound. Here you put in your superset. Then you do the 20 pages of calculations that this method tells you to do. And after that, it spits out a counting result, an answer to your question. And this whole thing kind of works like cooking. So if you put in bad ingredients, then you get a terrible, almost trivial counting answer at the end. So you would get something like number of triangle-free graphs as at most number of graphs, which is not very useful to prove that. But if you do a lot of work for the upper bound, and you put in effort into proving a good supersaturation result, put everything into it, then you should get a good counting result at the end. So conversely, if you apply the container method and you didn't get a good counting result, that's usually because your superset or your counting result wasn't strong enough. Okay, so basically these are the three steps that you want to apply to every single one of these questions, and you should always be able to get a good bound just by following these three steps. So I think the best thing to do now is I want to walk through one or two examples. How much time do I have, by the way? Like until
Half an hour?
So until 3?
Yes.
Okay. So I want to go through a few examples, and once you've seen this one or two or three examples, it should be fairly obvious how you would attack all these other problems by yourself. So what is the basic example that everyone who starts out with container method always learns first? That's the counting antichains. So how many antichains? Are there in the Boolean lattice? So that's the question we want to answer. Okay, so what do? We just follow those three steps. First step, we need an upper bound on the size of an empty chain. Well, luckily for us, that's very easy, because Sperner has proved that entries n over 2 is an upper bound on all empty chains, and this was done 90 years ago, so we don't have to do any work anymore. Okay, step 1 is done. Okay, step 2, superset. What does it mean? So in superset, we just have to prove that if a family is slightly larger than our upper bound, then it will contain many, many comparable pairs. So we want to prove that if family has size n choose n over 2 plus x, x can be anything, then it contains many comparable pairs in the family. Okay, so how can we do that? How can we prove that the family is slightly bigger than the middle layer of the Boolean lattice? It contains many comparable pairs. Well, if the family has size n choose n over 2 plus 1, then because of Sperner's theorem, we know that it contains at least one comparable pair. So, kind of by induction, by throwing out and putting back elements, you can easily prove that if a family has size n choose n over 2 plus x, then it contains at least x comparable pairs. Okay, so let's say this is what we want. So this is what we have. So proving this is very easy, so let's suppose that this is our superset. So now, step 3, applying the container method. This is the point where we take our upper bound, take our superset, plug everything into the container machine, and do the calculations. And if you actually go through the calculations here, what you get at the end is essentially the totally trivial upper bound, 2 to the 2 to the n, or something like that. So we get this as an upper bound for the number of empty chains. Yoo-hoo. Unfortunately, this is completely trivial, so this was useless. So why did we get a trivial result at the end? Even though we followed these 3 steps, he did everything as I told you to do, and yet he got something trivial. So the reason, as I said here, if you get a bad counting result at the end, it's because either your upper bound or your superset wasn't good enough. So in this case, our upper bound is definitely the best possible. That means that maybe this superset is not the best we can do.
Well, it
And
certainly doesn't look like many.
It definitely does not. Yeah, that's correct. And that's usually the case that if the superset you prove is totally trivial, that means that you will not get anything interesting out of the end. The bulk of the work has to be done in this step, basically.
So are you, you haven't said this, but if I give you 2 sharp bounds for both things that go in, do I get something
You don't-
non-trivial out?
You get what?
Do I get something non-trivial to come out?
Usually yes,
Okay,
but there is no guarantee that you'll get the best bounds.
okay.
So up to some error terms, we usually do get the best bounds, but sometimes for some reason we do not. So this
But I
is
shouldn't
just a
expect
technique.
it to be the trivial. I shouldn't expect it to be trivial.
No,
Okay.
definitely not.
Okay.
Yeah. Otherwise, this method would be a stupid method. No one would use it, right? It's just a fancy way to prove trivial stuff. Then. Okay, so we concluded that we messed up in the second step. We proved something trivial. Okay. So what should be the correct answer here? So here, this shouldn't be just x. This should be something more than x. So what should we expect to be the best correct term there? So if you think about it for a second,
Maybe like xn or so?
that is correct, yeah. Very good. So why is it xn?
Is the ideal case for Sperner's lemma is the middle rank. And if you add something in, the best thing to add is something very close.
Excellent, very good, very good. Exactly. What's your name?
Alex.
Alex. So as Alex said, the best thing seems to be if you just take the middle layer of the Boolean lattice, so this is the Boolean lattice, here we took the middle layer, and we have to take x more elements, so let's just take x elements above them. If you take an element up here that will be contained in many comparable pairs, that's not good, so this seems to be the best thing to do. Just take x elements on the layer above, and if you do that, then you get x times n over 2 plus 1 here. So x times n basically, as Alex said. And turns out that this intuition is correct. This is the best thing you can do. This is very, very, very non-trivial to prove this. But luckily for us, this is a theorem by Kleitman. This was actually a conjecture by Erdős and Katona from the 1940s. It was open for 2 decades until Kleitman proved it. And today, we actually know a one-line proof of this fact. This is just how mathematics evolves. So it's, at the end, if I have time, I want to show this proof. It's very beautiful. This is not Kleitman's original proof. Kleitman's original proof was using compressions, and it was quite involved. Okay, so luckily, now we have the best possible upper bound. We have the best possible superset. So now we should go ahead and apply container method. And if you do that, I will skip all the calculations now. You get that number of antichains is upper bounded by 2 to the n choose n over 2 times 1 plus some small term that goes to 0. Okay, so are we happy with this or are we not happy? Is this a good result? Is it far away from the truth? Or is it the best possible thing we can hope for?
Yeah, well, you've got that middle layer, and you're just taking the subsets.
Exactly, exactly. So if you just take any subset of the middle layer, then you always get antichains. So the number of antichains is at least 2 to the n to the n over 2. So this is actually correct up to the below 1 term. And then you can start worrying about the error term. I'm not going to go into that now. Okay, so this is probably the easiest application of the container method there is. But the other problems on this list were not much more difficult. So okay, so instead of showing another easy example, I will go for a difficult example now and try to show what could go wrong if you try to apply these steps and what kind of tricks you might need to use when applying this method. So a family in the Boolean lattice is called union free if it doesn't contain a solution to A union B equals C, where A, B, C are distinct sets. So for example, you cannot have 1, 2, 1, 3, and 1, 2, 3. This is not allowed to have all these 3 sets in your family. Okay, so people were interested in these families. First thing they were interested in is how large can such a family be. Let's start with that. How large can a union free family be? Okay, so this is the first question we want to answer. How many sets can we take without containing a solution to the equation A union B equals C? Can you see it from there?
Yeah, I can see that.
So, any guesses? For people who don't know the answer?
Take the middle layer.
Very good. Yeah, that's usually the answer to the questions in combinatorics. Just take the middle layer. So, for example, you could take middle layer, that gives us n choose n over 2 elements. Very good. Can we take more than that? Can you do n choose n over 2 plus 1?
I have a question. So, can A union B equal A, or is it C?
A, B, C are distinct.
Okay.
So these are distinct. So C should be different from A. Okay. Otherwise, it's just an antichain written in a fancy way, basically. So can you do entries n over 2 plus 1?
Yes, take the bottommost element, I think.
Empty set.
Very good. Yeah, take the middle layer and take the empty set, add it. Very good. Can we do entries n over 2 plus 2? You can keep going.
2 middle layers.
2 middle layers wouldn't work anymore, unfortunately. Anyway, so it turns out that you can take the middle layer and the sparse subset of the layer below that, if you choose them cleverly so that they are far enough from each other, then you will not make a solution to this equation. But it turns out that that's the best thing you can do. So, theorem, again by Kleitman, it says that union-free family has size at most n choose n over 2, plus maybe a little bit. 1 times 1 plus term that goes to 0, then goes to infinity. Okay, so now
Are
we
you
know
talking about an error correcting code for the small part, or is it different?
this small part. What do you
Yeah, for the small part, you for the sparse part, you need I.
Yes,
Or
exactly.
that's-
A one error correcting code, that's what we want. Okay, so now we have good upper bound on the size of these families. Now, next step is always how many such families are there. So this question was investigated by Uroš, Demetrovich, Katana, Kleitman, Sapozenko, and they proved in 91 that the number of union-free families is at most 2 to the n choose n over 2 times 2 root 2. So this was their upper bound for number of union-free families.
No little o.
Times 1 plus a little 1. Thank you. Okay, and they conjectured that this would be the correct bound, except without the 2 root 2 term. And that would be best possible then, up to the little 1 term then. Okay, so this property of being union-free obviously fits into this category, so we can attempt to do containers. Okay, so what happens if you try to apply containers? Well, step 1, Kleitman already did it for us, as always. This is usually the case with the first step, that if you're interested in counting families that satisfy some property, that's usually because you already know how large these families can be. Because Erdős or Katana or Freddy or Kleitman have done it 50 years ago already, or something like that. So that's what usually happens. So you just start with step 2, supersaturation. You want to show that if a family has size bigger than n choose n over 2, then it contains many, many solutions to this equation. So I want to show that if f is at least 1 plus epsilon times n choose n over 2, then it contains many solutions to A union B equals C. Okay, how would you do that? So this is not so easy anymore. If anyone knows the answer like this, I will be very impressed. So the best thing you can do here is look at the proof of Kleitman, that's n choose n over 2, that's 1 plus over 1 is the best, and try to keep working, keep punching it until eventually it gives in, and you can actually prove it that it contains n squared times n choose n over 2 solutions, basically. Which in some sense is the best possible case, because again, as Alex said, the best thing to do seems to be take the Boolean lattice, take the middle layer, and just a bunch of elements above it, and then each element gives rise to n squared solutions roughly, and it turns out that in some sense this is the best you can do. Okay, so we have supersets, we have upper bounds. The problem is that if you put these two into the container method, you get a trivial bound. The question is, why did you get a trivial bound? Even though you put in the best upper bound and the best supersaturation.
Because of the 2 root 2.
No. So they obtained the 2 root 2 upper bound with some totally different methods. And it turns out that their conjecture was correct. This 2 root 2 really shouldn't be here. So it was just that they didn't.
Wrong.
Yeah. So it's not because of the 2 root 2. So we put in the best possible upper bound, best possible superset, and yet we get a counting result that's worse than this bound. And that's because if you just look at this problem in this way, then so it's basically because the container method machine that you put it in wasn't the best thing you could do. So basically what goes wrong if you apply the container method, which will be a bit hard to explain because I didn't tell you what actually container theorem says, but I will try. So basically what goes wrong is that if you look at this equation, A union B equals C, and someone comes along and tells you what A and C are, depending on what A and C are, it could be that there are many options for B, or it could be that there are few options for B. So, for example, if A is elements from 1 up to n minus 1, and C is all elements from 1 up to n, then for B there are basically 2 to the n, so 2 to the n possibilities. Something like 2 to the n minus 1 options for B. But if A is the empty set and C is the whole thing, then it turns out that there are 0 options for B. So the problem with this property was that it's not symmetric in this sense. Even though it looks symmetric, depending on what A and C are, there could be many options for B or very few options. This turns out to be a problem when you actually try to apply this algorithm. But there's a very easy fix for that. That took us ages to find, but it's completely trivial once you know what this trick is. So the key observation was the following. So here's the key idea, which will sound very stupid, is that even though if someone tells you A and C, there could be many or few options for B, but the other way around it doesn't work. So given A and B, C is determined. So there is at most one option for C. Okay, so what does it mean? It means that even though in this hypergraph that you construct on these sets, where the edges correspond to the solutions to this equation, the co-degrees are all over the place, depending on A and C. The co-degree could be small or huge, but if you look at this hypergraph in kind of a directed way, where each hyperedge is kind of directed in this way, then every pair has co-degree exactly 1. So then the hypergraph becomes totally symmetric suddenly. And once your property is symmetric, you can go ahead, apply the container method, and if you do it this way, so kind of a directed application of the method, you can actually prove that the number of union-free families is at most due to the edges n over 2 plus 0 term. So basically this is how it usually goes with container method proofs. So the hard part is usually the superset. You work the superset, work until you get the best possible superset. Then you try plugging in everything into the container method and pray that it will work out. And if it doesn't work out, then you have like 3 or 4 tricks that you could try to fix it. This is one of them. That your property was really a directed property, or something like that. And there are a couple more that you could try. But basically, these are all written down in very nice tutorial articles. The part that's not written down anywhere, because there is no general method, is the supersaturation part. So the step 2 is really usually the hardest one, because for every problem you need new methods to prove these kind of statements. And there are a bunch of more or less general methods, but nothing like really general. So this is the hard part. And so I have 5 more minutes, so
Excuse me.
yeah.
Is it possible to work backwards? Put something.
Yeah, absolutely. So by working backwards, you can kind of figure out what is the supersaturation statement you want to prove. That's true, if that's what you meant.
So have you tried putting, like, working backwards with this bound to look at the supersets?
What do you mean? I don't think I understand it. So what do you mean?
This bound that you have here, you said that you couldn't get it with putting the best superset into
Right.
the
Right.
container method.
Well, it was until they
Yeah, but
They
then we
added
fixed
this
it.
directed idea.
So then we looked at it in a directed way, and then we managed to get the best possible result. Yeah. So working backwards, you could kind of try to figure out what is the supersaturation that you want to prove, but nothing more really. So that's the only thing you could do. So in the last 2 minutes, I just want to talk very briefly about what kind of methods we have for proving the supersaturation statements, because the problem is that there is no one general method, but there are some more or less general things that you could do. So for Sperner times things, every time you are faced with a Sperner type problem, whatever that means, so kind of antichains, or even having or not having solutions in the Boolean lattice, what you want to do is hit the base set with a random permutation and take expectations. So basically, look at the original proof, get some randomness involved into it, look at what happens in expectation, and bam, magically you suddenly have supersets. This is a very nice method. The second most useful method, well, the most useful method is always look at the original proof and try to modify it. This is the second most useful method. The third most useful method is averaging arguments. This is when you try to forget everything you know about mathematics. You just take your upper bound and try to do some averaging all over the graphs or your families. So with averaging arguments, you can tackle problems that involve how many subgraphs appear if you cross the maximum bound. So with this you can find many h subgraphs of some fixed graph G if G has too many edges. Okay? So if number of edges of G is more than is allowed for an H-free graph, then by averaging you can actually find many, many subgraphs. And there is one more technique that, 1 minute for that. This is called Freddy lemma, which is this magic technique that basically if you have no idea how to prove a supersaturation statement, then this is what you go to. This just says that the number of cherries in a graph is always bigger than the number of edges in a graph, minus n or something like that. And basically if you build a graph in the right way, then this can immediately give you a supersaturation statement. And there is one more that these two should be switched up. If you do some algebraic graphs, or you know the eigenvalues of the graph, you can do some expander mixing them and stuff. Okay, so I think these are the 4 or 5 main techniques to prove superset. And these are usually the hardest part of the proof. If you manage to prove supersets, then you can always go ahead and apply container method and get some kind of bound to it. So yeah, I think I will stop here. So thank you very much.
Questions?
Yeah.
Could you tell us the one-liner for if the family has n choose n over 2 plus
Oh,
x?
yeah. So I lied with that
Like
one line. It's more like 10 lines.
Oh.
I can tell you. I
Yeah,
can tell you afterwards. Definitely.
I think you know that.
Yeah, well, yeah, maybe I
That's-
know that.
It's a beautiful proof. Such a beautiful.
Symmetric chain
Yeah,
computation?
that's right.
Okay, now I know it all.
Yeah, of course. Yeah, Alex.
You had mentioned Balogh as one of the people who recently used the technique.
So he was the one who. So these two sets of authors were the ones who developed this technique to work for hypergraphs, basically.
Before this directed improvement of the algorithm was added, I think they got some sort of result on counting Sidon sets, and it seems like
They did. And
and was it using this trick?
not this directed trick. No, they were using
Not
a
the
slightly-
directed trick, but because the equations there are
they were using container
homogeneous,
methods.
they're not. There's like there's exactly one way
Yeah.
to solve the equation,
Mhm.
so they would be uniform in that sense.
Right. So they were definitely using container methods. They were using some tricks that I'm not entirely familiar with right now. But yeah,
But yeah, they just wouldn't run into the same problem with this.
I guess no, because it's completely symmetric, those
Yeah.
forbidden things. Yeah, I guess so. Yeah.
So can you say a little bit about why you need the minor, the monotone property and the forbidden property?
Because I want the family to be easily characterizable by what is forbidden. So why do I want an easy description of the forbidden stuff? Because I want to build a hypergraph where the edges correspond to the forbidden objects. Okay? And if a property is easily characterized by, if a property is characterized by what is forbidden, then it's always monotone. So it's actually the first, stating that it's monotone was not necessary. It was implied by the second line after that. Yeah, good question. So
But that's needed in
yeah,
the
it's
black box
definitely-
part.
it's needed for the part where we say that. So when I say that the property can be described by what stuff is forbidden, then that implies that the property is monotone. Because yeah, and that's needed in the black box part.
Okay.
After that. Yeah.
Okay. Yeah. That's what. That's
Yeah,
what
yeah,
I was
yeah, that's right. Yeah.
Is there like one or two sentences about how the black box is applied? You're saying you build some hypergraph?
Yeah, so 2 sentences about black box. Okay, so for example, I want to count families that don't have solution to this. So union-free families, what do? I create a graph with a hypergraph with vertex sets being Boolean lattice, and edge sets correspond to solutions to this equation. And then a union-free family directly corresponds to an independent set in this hypergraph. So we just have to find a clever way to count independent sets in some hypergraphs. And that's what the container method really does. It just counts independent sets in hypergraphs in a very, very tricky way. And if I had half an hour more, I would be able to explain to you what this black box is. It's not that complicated. It's just that I only had 15 minutes now, and I was just trying to build some intuition on how to apply this technique. Okay.
Other questions? Okay. Let's thank Adam again.
Thank you.